What generally matters to us is not the absolute potential at one point, but its relative change between 2 points. Think back to the cyclists and the mountain race. They don't care what their absolute altitude is. All they really care about is the height they have to climb from the beginning to the end of the race. Here we see the difference is called potential difference delta V. It is also measured in volts. The expression for potential difference doesn't depend on the path taken from A to B, it only depends on the positions of the start and end point. To understand why, we look back at equipotentials. We know that the electric field lines around a positive charge radiate out from the charge. The equipotential surfaces will be spherical shells that are perpendicular to the field lines. We know too that you don't do any work moving along an equipotential. You only do work when moving along a field line. So for any 2 points in the field, call them A and B, you can make the path between them into a combination of moving along equipotentials and moving along field lines. And for the field, you can see it only depends on the distance from the centre. I could have chosen a different path from A to B, and still only the components along the field lines would count, so the result would be the same. Let's have a look now at an example of finding the potential difference between A and B if the central charge is 1 microcoulomb, A is 1 metre away, and B is 2 metres away. Let's start with our point charge here, Q, that is 1 by 10 to the minus 6 coulombs. And we're interested in a point A that is 1 metre away and a point B that is 2 metres away. And we are interested in the change in potential as we move from A to B. So that change or potential difference will be just the potential at B minus the potential at A. And we know that in terms of the electric field, that is the integral going from A to B of E times ds. Now let's remember that for a point charge, E, which is F over Q naught, is just going to be Q over 4 pi E naught R squared. So that means our potential difference will be minus, going from 1 to 2, Q over 4 pi E naught R squared dr. Now we've seen the integral of 1 over R squared done quite a few times now. As usual, we'll bring all the constant terms out the front. And we're now integrating 1 over R squared dr. And that will simply be minus Q over 4 pi E naught. The integral of 1 over R squared is minus 1 over R. And that is evaluated going from 1 to 2 metres. So that will be minus Q over 4 pi E naught. The value at 2, which is minus a half, minus the value at 1, which is minus 1, so that makes it a plus 1. So let's put in all our values now. We have the minus still. We have 1 by 10 to the minus 6. We have 4 pi by 8.854 by 10 to the minus 12, and we times that by a half, and that gets us, when we work out all of that, minus 4.5 by 10 cubed volts, or minus 4.5 kilovolts. Why is it a negative number? because we've moved further away from a positive point charge, and that means we've moved in the direction the force would push a positive test charge, so we have gone from a higher to a lower potential.